Hello everyone, I am Zinat and I am thrilled to have the opportunity to present our work, a comparative evaluation of visual summarization techniques for event sequences. This is a collaborative effort between myself and fellow researchers Jinhua, Arjun, Nistha and Professor Zhicheng from the University of Maryland. So event sequence data is basically events connected by a common entity. They are ordered temporally to form sequences. They contain categorical event information along with temporal data. Event sequence data is found in many application domains. For instance, electronic health records often contain event sequence data. Here is an example of such event sequence data, where an event sequence summarization technique, EventFlow, is used for task performance analysis. In pediatric trauma unit, the trauma team is required to complete a series of steps in a very specific order. They should check the patient's airway, then breathing, check for circulation, and then check for disability. Then they scan head to toe to detect any external injuries. In the trauma dataset, we may ask the question if these steps are being properly followed by the practitioners. Here we can see a simple aggregation of events generated by EventFlow. Even though we can see all the events in the same diagram, it's difficult to identify the patterns of deviation from the protocol. Here we can see a visual summary that has been manually filtered only to contain the ABCDE events. The summary contains far less events and the patterns are also identifiable. We can see sometimes breathing is measured first, sometimes secondary survey is measured before disability. Overall, in more than half of the sequences, there is a deviation from the protocol. However, manual summarization requires effort and is time-consuming. Therefore, to reduce manual tasks, extensive research has focused on techniques that automatically extract important events and patterns from a dataset and display the extracted results in a concise visual summary, where the results contain much fewer events and sequences than the original dataset, and provide an at-a-glance overview of the dataset, making it easier to interpret. It's no surprise that researchers in visualization have created many ways to summarize and visualize sequential data. These summary techniques visualize the summary structure in different ways. Here is an example from a toy dataset, where the same dataset is visualized as a graph, as a set of linear sequences, and as a tree by different techniques. Even for the same summary structure, techniques may use different mining methods to find patterns. They can also vary by granularity or level of detail. For example, both the left and right figure have the same summary structure, but the contents are different. The left figure has a finer granularity and the right figure has a coarser granularity. Now, the question arises, which technique is best suited for our needs? To find an answer, we surveyed 14 event sequence visualization techniques published over the past 8 years. 13 out of 14 evaluated the proposed techniques through qualitative case studies with domain experts. While case studies show validity of work, they lack objective comparison between techniques. Only CoreFlow compared with other techniques, but it only showed sample visualizations. To date, there has been no systematic evaluation available to compare event sequence visualization techniques. The lack of systematic evaluation is problematic. Researchers have no established method to measure the performance of new techniques. Practitioners have no guidance for choosing a technique for their data and analytic need. In our work, we address this gap by developing a method to systematically compare visual summary techniques. There are a few challenges that make it difficult to compare event sequence visualization techniques. First, a visualization system is made up of several components, such as the algorithm, interactivity, and visual design. Secondly, previous studies on visualization effectiveness typically focus on graphical perception. However, in our case, we perform significant data reduction before creating visualizations. This means that just focusing on graphical perception doesn't fully capture the importance of the data reduction step. Finally, low-level tasks such as looking up and comparing data values do not shed light on the quality of the visual summary. To resolve these challenges, we take the following approach. First, we focus on evaluating the algorithms, not the entire systems, with its user interface and interactivity. Also, different designs in the original papers may introduce confounding factors. Therefore, we adopt our own visualization design. To address the second challenge, we designed the study to account for both the summary structure or visual design and the summary content or the extracted patterns. For the final challenge, we use an insight-based approach where the participants judge how well the visual summaries created by different techniques represent a pre-formulated insight. It is not possible to compare all the available visualization techniques in a single study. So, we decided to compare 3 techniques. Now, I will explain how we selected these techniques. First, we wanted the techniques to be domain agnostic. They should be able to handle datasets from different problem domains. Second, we required the techniques to be automated. Third, the techniques should have some data reduction component. Generated summaries should consist much fewer events and sequences compared to the input dataset. Fourth, the technique should support controlling the granularity in which data is represented in the summary structure. Finally, each technique should have a different summary structure. Now we present the techniques we used in the study. We want to include 3 types of summary structures: linear sequences, dedicted acyclic graph, and tree. For linear sequences, we use sequence synopsis. Sequence synopsis uses the minimum description length principle to cluster sequences and identify a representative pattern for each cluster. For directed acyclic graph, we use SentenTree. Although it was originally designed for text data, it can be applied to event sequences. SentenTree uses a rank and divide approach and generates a DAX summary. For tree structure, we use CoreFlow. CoreFlow uses a recursive rank-divide-trim algorithm and generates pattern in a tree format. To eliminate the potential confounding effects, we did not follow the original visualization designs. Instead, we chose a minimalistic and consistent design for the visualizations. Each event is shown as a node with a label. Events connected by links form a pattern. Numeric labels represent the number of sequences with that pattern. The vertical position represents the order of events going from top to bottom. The width of a link is proportional to the number of sequences. The same color scheme is used across techniques for consistency. We can control granularity level by adjusting minimum support or the number of sequences parameter in the UI. Mentioned in the technique selection criteria, all the techniques we use supports parameterized tuning of summary granularity. After experimenting with varying degrees of granularity, we decide upon using 6 granularity levels. For CoreFlow and SentenTree, we use minimum support parameter. For sequence synopsis, we use the number of patterns parameter. Here are the criteria we considered for dataset selection. First, we wanted to include datasets from different areas of application. Second, we searched if any previous studies using the dataset contains ground truth. To reduce bias, we excluded datasets used in any of the 3 original papers. Out of the 15 datasets we collected, we selected 6 for our study. Here are the 6 datasets with corresponding domain information. However, no established benchmark ground truth on the dataset is instantly available for evaluation. Therefore, we curated associated insight from corresponding publications and supplemental videos. Thus, we identified 3 insights per dataset. Our curated insights lead to 3 high-level analytic tasks: common pattern identification, clustering, and anomaly detection. Take a quick look at the variables in our study. We have 3 analytic tasks, 2 datasets per task. Each dataset has 3 insights and can be broken down to 6 granularity levels. We have visualizations from 3 techniques for each level. This means that we have a total of 324 unique combinations. It is not possible for a single participant to experience all these combinations in a reasonable amount of time. So, each participant sees 3 insights multiplied by 3 techniques equal 9 combinations in total. After deciding the assignment for each participant, we are left with 36 unique combinations. We assigned 5 participants per condition, resulting in 36 multiplied by 5 equals 180 total participants. Having such large number of participants in lab is difficult. Therefore, we opt for a crowdsourced experiment. It is difficult to assess participants' capability to read visualizations in a crowdsourced setting. We developed a 3-phase evaluation process to ensure the participants have adequate visual and data literacy. The participants first complete a tutorial and a pre-screening test. They proceed to the main experiment if they satisfy the pre-screening criteria. In the tutorial, the participants click through a series of displays which highlights different attributes of the visual summaries. Here is a screenshot from the tutorial. In the pre-screening, we ask 6 questions on a dataset to test the participants' visual literacy in various low-level tasks. Those answering at least 50% questions correctly proceed to the main experiment. For the main experiment, we provide the participants with a brief description of the dataset and the problem domain. In each of the following pages, the participant sees an insight and one visual summary generated by one of the 3 techniques. The participant rates each technique on a 7-point Likert scale. They also provide a text justification for the ratings assigned. We perform our evaluation based on the following collected data: a 7-point Likert scale rating, completion time for each of the rating, and one text justification for each technique. The first two help us quantitatively compare the techniques, while text justification makes qualitative analysis possible. Let's take a look at our results. In this chart, we can see the distribution of ratings for each of the visualization techniques. For instance, 33.7% participants strongly disagreed that the CoreFlow summary structure effectively displayed the presented text insight. The table below shows the average Likert scale rating for the techniques. Sequence Synopsis is the best among 3, with a rating of 3.86. Here, we can see the Likert scale rating distribution broken down by task. On average, Sequence Synopsis performs best for anomaly detection, clustering, and common pattern identification. Therefore, it is the best performer for all 3 tasks. Here is the ranking for the 3 techniques in terms of Likert scale rating. Sequence Synopsis takes the first position, followed by SentenTree and CoreFlow. Here, we can see a box and whisker plot showing the completion time distribution for each visualization technique. The table shows average completion time for the techniques in seconds. Please note that for completion time, smaller value indicates better performance. On average, it takes lowest time to rate CoreFlow visualizations, around 48 seconds. Similar pattern is observed across all 3 tasks. CoreFlow has the lowest average completion time for anomaly detection, clustering, and common pattern identification. Here is the ranking for the 3 techniques in terms of completion time. CoreFlow takes the first position, followed by SentenTree and Sequence Synopsis. We built a linear mixed effect model to identify factors influencing human performance. We observe technique has a significance in both metric. Task is not a significant predictor of Likert scale rating or completion time. Granularity is important for completion time, which makes sense as finer granularity indicates more events are present in the summary, so it takes longer to interpret the summary. We performed open encoding on the collected text justifications from 180 participants. This helps us understand the reason behind summary quality assessment. Now I will demonstrate how we performed the encoding. On the right, we can see a justification by a participant. We tag the facts were not shown in the image as missing key event and numerical discrepancies as numbers do not match text description. Here is another comment that falls into the easy to understand category. We identified 8 total tag categories with 799 total tags. The Merrimaker plot on the right displays the tag categories, with category height showing the percentage of total tags associated with that category, and technique width showing the share of techniques within that category. As shown in the example, one comment may have multiple tags associated with it. Most comments touched upon 2 overarching themes covering the tag categories. The first theme is content, how closely the patterns in the visualization match the insight. Describes if important events and associated quantitative information are included in the visualization. The second theme is interpretability, how easy it is to read the visualization. We identified 4 tag categories associated with content based on if the summary contains key events and if the numbers match the text description. Sequence Synopsis outperforms the other techniques in terms of key events. It is also the best in numeric information accuracy. Interpretability indicates how easy it is to read the image. We identified 3 tags related to interpretability: easy to understand, difficult to understand, and overlapping branches. Notice that all techniques have almost equal share in both easy to understand and difficult to understand category. Further analysis shows interpretability varies with dataset and granularity, which is not perceivable from the summary figure. Here are our findings from the comments. Both CoreFlow and SentenTree have branching patterns. Some participants liked CoreFlow for its simplicity. Some found it easy to find anomaly following branches in SentenTree. However, for some participants, the branching patterns were unfavorable. Overlapping branches are a prominent issue in SentenTree, which led to confusion and difficulty of understanding for many participants. We see similar mixed reactions toward the individual linear sequences in sequence synopsis visualizations. Some participants prefer the distinction of linear sequences in sequence synopsis. On the other hand, some participants do not favor linear sequences as the individual bars are confusing to them. Note that sequence synopsis has no text related to overlapping branches, as it has linear sequences only. From our analysis, we see task completion time is inversely correlated with technique ratings. Sequence synopsis obtains the highest ratings but requires the longest comprehension time. On the other hand, CoreFlow has the lowest ratings due to omission of key events but requires the least comprehension time. Balancing summary complexity and accuracy is crucial for all visual summarization techniques for event sequences. From our multifaceted analysis, we see no perfect visual summarization technique for event sequence data exists. There is still room for improvement in accuracy, computational resource uses, and interpretability of visual summaries. Our study evaluates the effectiveness of three techniques holistically. Each technique has multiple components, including data reduction method, visual designs, summary structure, and interactivity. All these components play important roles in technique effectiveness. In addition, individual dataset characteristics also play a role in technique effectiveness. In our work, we only focus on data reduction method and summary structure. Moreover, we assess the effects of these components holistically. Further study is required to assess the effects of the individual components and their interactions on visual summarization outcomes. To summarize, our work makes the following contribution. Experiment design. We designed the first study of its kind to comprehensively compare the effectiveness of visual summarization techniques for event sequence data. Insight-based method that we use can guide future evaluations of new and existing techniques. Result analysis. Our multifaceted analysis results offer understanding of technique performance, trade-offs, and areas of improvement for new techniques. System implementation. We re-implemented 3 existing automated event sequence summary techniques as well as 3 different approaches to visualize summary structures. We plan to open source the code for public use. Thank you so much for listening to the talk. Please refer to our paper to learn more about our work.